Okay. Okay. So we defined probability space as follows. We defined a probability space and we defined conditional expectation, independence, and we looked at some example. So let me recall the general definition of general probability space. So let omega be any set, any set. Okay. Then we say this is a subset of the power set of omega. Script A is a subset of power set of omega. It's a sigma algebra. By this we mean sigma algebra means omega phi is in A and it is closed under countable union, countable intersection, which will follow from here, and complements. It's a collection of sets in the power set, which satisfies its closed under countable union. That is, if A n. It can be finite. You can take rest of the ANs as empty set, then it will be a finite collection contained in uh, A implies union of AN, intersection of AN. They are also in A. And if A is in A, then A complement is in A. This is what is called a sigma algebra. Okay. Then a probability measure we have defined already, P from script A to 0, 1. So it is defined, I mean, if it is discrete, you can define for points. I mean, you can go back and if from this P, you can go back to points, and from points, you can come by summing over the set. Otherwise, you cannot define, I mean, you cannot use points if the space is continuous. So for that, we do, I mean, the probability measure is generally, it's a function from script A, the sigma algebra to 0, 1, satisfying these properties such that omega equals 1, P of empty set is 0, and P of, as I have already introduced in notation, if we have a disjoint union, then that is summation of A. Okay. So this is what is a probability measure. So let us see an example of general uniform probability measure. We have already seen one. We will not give a correct, I mean, I will give an example, but I will not be proving that it actually defined on whole of A. That requires measure theory. Okay. So you can take omega to be this. Okay. What is script A? It is some sigma field, okay, which contains open intervals, okay, which contain intervals. Okay. Script A contains all intervals. It is some sigma algebra which contain all the intervals. We will be only defining on intervals. You have to assume that, I mean, it's later, it will be proved that there exists sigma algebra where these things are well defined and all those things. Okay. There exists the sigma algebra is not very complicated. I mean, you can take, I mean, generally you will not be knowing all the sets in a sigma algebra. If you define some sigma algebra, it will be difficult to enumerate. I mean, for enumerate means like intervals. We know all the intervals, how it look like. We may not know all the sets in a sigma algebra, but that's not the point. Abstractly, it exists. Okay, so you can take the sigma algebra generated by all intervals. Okay, there is already a sigma algebra. Power set is a sigma algebra. Okay, so there is already a sigma algebra. You can take the all sigma algebra which contains. So there is a sigma. There exists a sigma algebra containing intervals. So you can take the intersection of all sigma algebras containing the intervals. That will give you a sigma algebra. That is what the sigma algebra generated. Smallest sigma algebra which contains all the intervals. Okay, which is usually called as Borel sigma algebra. We will not need all those things. We will just work with interval. We assume that there exists a sigma algebra where all intervals are there. Okay, then we want to define on basically on the interval or any set where this makes sense. Okay. Then you can define P of any A to be equal to any A means maybe intervals. Okay, P of any interval AB. It can be closed interval, half closed, half open, doesn't matter. Okay, so it is just B minus A. Okay, where A by 0, less than or equal to A, less than or equal to B. It can be, if it is equal, it will be empty set. But then if you take some half open, I mean, closed interval or something, it will be singleton. Singleton will be 0 and it's 1. Okay. You can define, this is just the length of the interval. Okay. This is the probability. Probability of any interval is B minus A. That's all. Okay. This is what is called uniform probability distribution. We will define what is a distribution is, but this is what, say, it's called uniform probability. Continuous uniform probability. Okay. This is on the interval. I mean, you can define it. For example, you can take AB, interval AB itself. Then you can define for any interval xy. You can define it to be y minus x by b minus a. Okay. This will also be a probability measure. Closed interval, it will be the same. It will be the same for any interval, closed AB or any half open, half closed, anything. Eh? Because the probability of whole set would be 1, no? That's why. Okay. That's what I have. See, this is the next example. You have written. Okay. So you can take it for anything. In general, you can take in R2 or R3 or even Rn, you can define this thing. Take the, I mean, then you have to go for volume. In R2, you can take any set in R2. Okay. Then you can, so your omega is S. Okay. Then for any A contained in S, wherever this makes sense, okay, I'm not defining rigorously, wherever this makes sense, you can define probability of A equal to the area, wherever area makes sense. Area does not, need not make sense for everything. Area of A divided by area of S. Okay. This is also called uniform probability distribution. Okay. If the area of S is 1, this is just the area. Okay. If the area, if the whole set is 1, then this is just the area. Okay. Okay. So then we proved this. Let me recall because we went too fast in the end. Let me just prove this. So this is the proposition. And just I will quickly go through this again. Okay. If you have a probability space, omega, P and P, this is how a probability space is written. Okay. Probability space means it contains three objects, a sample space, it's a sigma algebra, and a mesh probability function, which is defined on the sigma algebra to 0, 1, the interval 0, 1. So this is what is called a probability space. Okay. Then if you have a AN, a collection of countable collection contained in A, okay, such that ANs are increasing, AM like this. Okay. AN plus 1 is contained in AN is contained in AN plus 1 is enough for all n. Okay. This is enough. Okay. Then so A equal to union of AN. This is what is usually called as this is written as AN increases to A. I mean, AN is contained in AN plus 1, contained in AN plus 2, and the whole thing increases to A. You just take the union of this thing. This is just all elements in omega which are in any one of those ANs. That's what it means. Okay. There is no result. There is if no, not then. Okay. There is no if. If, yeah, this is all if. Okay. Now I wanted to write here, then for, I mean, then for I wanted to write. I want to write the result, then I have to define A, I remembered, so I wrote it. Okay. Then for, I mean, for A, then, okay, then P of A equal to limit of probability of A. We already know that the probability function is a monotone function. That is, if A is contained in B, probability of A is less than or equal to B. So P of AN will increase. This just means P of AN, I mean P of A, which is equal to supremum of P of AN. Okay. That is, A of AN will increase to P of A. Okay. This is one. Second thing is, similarly, if you have a Bn contained in A and Bn decreases to B, that is Bn plus 1 contains Bn and intersection of Bn, this is for all n, and intersection of Bn equal to B, okay, then probability of Bn also decreases to probability of B, okay. That is probability of B equal to limit of P of Bn, which is equal to infimum of P of Bn, okay. So from here, this will follow by taking just complements. Okay, that's clear. Okay, you take the complement with the, so please check it. And for this, we have used the following. Maybe I'll just write it. You just define one, proof of one. You're not writing properly. One, you just take some dn equal to an minus an plus 1. Sorry, an plus 1 minus an, which is equal to an plus 1 intersection an complement. Okay? That's the definition if you want. You are just removing this set. Then union of k equal to 1, maybe n equal to 1 to n dn is same as an. Okay? And disjoint union of dn n equal to 1 to infinity is again equal to a. But then this implies summation p of dn equal to p of an. Okay? P of this implies summation equal to an. Okay. Now this is equal to, so this, I mean, this is equal to this. This implies p of a equal to summation n equal to 1 to infinity p of an, which is equal to limit n goes to infinity, summation n equal to 1 to infinity p of an, n equal to 1 to here n, and this is equal to limit of p of an. Okay, n goes to, right? That's all. We have just used that there. Okay. That's all. So we have proved it. So it's direct. You just write the increasing union as some disjoint union, and from the additivity property of the probability measure, this follows. That's all. Okay. B n plus 1, that's right. I wrote the same thing, right? Yeah, that's why I put the n plus 1 here, but then I reversed. Okay, you are right. Yeah, good. Yeah, you should be watchful. Okay, I may make many mistakes. So like this, silly mistakes, you should tell me. Okay, so this is something we noticed. It's just an observation. This is like the probability function is continuous. I mean, it's a function on sets, but it's like some sort of continuity. You can actually define lim inf of set, lim sup of sets, and define to the sums. I mean, for any sequence like that, any sequence an collection of sets need not be increasing, need not be decreasing. You can define lim inf and lim sup, and then you say the limit exists if lim inf and lim sup of sets are equal. Then also this limit will converge. Okay, then it will not be increasing. P of n will not be increasing. P of an will not be increasing or decreasing, but then the limit will exist and that will be equal. Okay, so if I feel like, I will give that as an assignment. Okay, I will define lim inf, lim sup, and give it as an assignment. It's very direct. Proving it is very direct. Okay. So then we defined conditional probability. All those are same. We discuss only discrete probability examples, discrete examples, but it's same for continuous also. Okay, there is no difference. The conditional probability or independence, we define independence as follows. So we were discussing in the last class independence. So we have a probability space in the background. Then we say A, B, two sets. A are independent. This is the same as any probability space, need not be discrete or anything. Then P of independent if P of A intersection B equal to P of A times P of B. That's all. Which is equivalent to saying if you take the conditional probability of B given A is P of B itself. PA given conditional probability of A given B is also P of A. So this will imply from this will follow from this. Okay, it's equivalent to this. And independence, we discussed one or two examples. And this is just to, this is again a finite probability example. This is just to show that two events which look like same, one will be independent, the other will not be independent, and it's clear why. If you throw a dice twice, then what is the omega? Omega is 1, 2 up to 6 cross 1, 2 up to 6, right? There are 36 elements. Okay, you may get one among this number, you may get one among this number. So there are 36 possibilities. Okay, then the probability of the event, I already gave an example using this, that mutually independent does not, pairwise independent does not imply independence for n number of sets, n number of events. So now if you take probability of sum of the two throws, sum is 7. Okay. This is, you called it, I mean, you take this set, A equal to, the sum is 7. Okay. AI equal to the first result of sum is 7 and when you add in the both the throws. First throw is I. Okay. Then you can see that P of AI for any I is going to be 1 by 6. Okay. Probability of sum is 7. There are 6 such things. 1 plus 6, 2 plus 5. There are 6 of them. That is also 1 by 6. And probability that you have ith element here and then the sum is 7 is again 1 by 6. There is only one possibility and there are 1 among 6, right? Right? So there is only one here. There are, okay. No, 1 by 36, sorry. Probability of A is 1 by 6. Probability of AI is 1 by 6. Okay. Probability of A intersection AI is 1 by 36. Okay. Now you take BI, B equal to, sum is 8. Okay. And just to show you that probability of A1 intersection B is 0. Okay. If even 9, everything for this is true. Okay. For 9, A1 is 0. On the other hand, P of A1 is 1 by 6. P of B is, there are some 5 by 36. A intersection A means you get some ith point here. There is only one here. There are 1 by 36. We are using what is called uniform probability in this. Okay, every outcome has equal probability. So from that it follows. Okay, there should be summation here. Correct. Yeah. Capital N equal to 1. Then is equal to P of A1, which is equal to P of A1. It's okay. One you assume A0 is empty. Last time also this problem, if you want. When you want to, if N is 1, then you are deducting start from 0. Which way? No, you just, I mean, it is just, I'm talking A1 equal to D1, A2 equal to A2 minus A1. Go on like this. That's all. First one is just D1 itself. That's why I'm saying take A0 to be, there is no A0. You have to subtract the previous one. You can take it to be empty if you want. If you remove empty set, you will remove. Oh, okay. 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 Well, you know, this is a proper mistake. This is the right definition. Okay. Yeah. Okay. That's a good question. Yeah. It is AN minus AN minus. Okay. That's correct. Okay. So here it's not the case. So, I mean, this is independent. That's not independent. Okay. There are examples in continuous case also you can say. Mm, okay. So one thing very easy to note is if you take any event here, any event which is a subset of this, there is nothing like it's a subset of this, subset of this. I mean, if you want to take consider subset of this event, that should be that event times omega. I mean, everything is a subset of this product space. Okay. So in this example, A is contained in 1 up to 6. Maybe A you have used. C is contained in this. Then C cross, you call this as omega 1, call this as omega 2. Okay, C cross omega 2, which is contained in omega 1, omega 2, and some C1 cross omega 2, C1, C2, and omega 1 cross C2. They are anyway independent. Okay. Probability of this set will be number of elements here divided by 36. Probability anything here, no, not this by 6, sorry, 6. 6. Probability of this is equal to probability of C1 into probability of this 1. See, if you take any sets here, C1 cross C2 contained in omega 1 cross omega 2, then probability of C1 cross C2 is P of C1 times P of C2. Okay. By definition. Okay. Yeah. So C1, so C1, C2 doesn't make sense in here. So you have to take C1 cross omega 2, omega 1 cross C2. Okay. So this will imply that omega 1, C1 cross omega 1 and omega 2, omega 1 cross C2 are independent. Probability of this is P of C1, probability of this is this. Okay. Their intersection is C1 cross C2. You just write the definition. This is all those, I mean, you should verify this. If you are not convinced, you should sit and verify this. C1 cross omega 2 is all those tuple xy, where x is contains in C1, y is in omega 2, anything. Similarly here. Then their intersection, x will come from here, y will come from here. That is the intersection. So that is exactly C1 cross C2. Okay, if you write it, it will be clear that this intersection is C1 cross C2. Okay, so that probability is probability of C1 times probability of C2. So this in this setup, in any, I mean, in any probability space, this is true. Exactly, everywhere. So let me just write it. The continuous case, it's not easy to construct the product measure. Okay, that's all. If you have omega 1, A1, P1, and omega 2, A2, P2, are probability spaces. Okay. Then you can take omega 1 cross omega 2. Okay. But then A1 cross A2, it's something different. That is the sigma algebra A1 cross A2. You don't have to really understand this, but this is sigma algebra generated by A1 cross A2. A1 cross A2 is something. That is just, but that will not be a sigma algebra. You have to take the sigma algebra generated by this. Okay. That will be this. Then this, we have a measure P1, P2. We will only consider the finite case. Okay. It will not be a sigma algebra. You can check it. For example, if you take real line cross real line, okay, all the sets in this are just squares, rectangles. Okay, but that sigma algebra will contain circle, very complicated things. Okay, so it will not be that. It will contain it contain all regions, all open sets, for example, all open regions, everything. Okay, so sigma algebra can get very complicated. Even all open sets are very easy to describe, but it's much more than that. Okay, so because of that, this sigma algebra is very big. I mean, you just have to take sigma algebra generated by this, whatever it means. Okay, but we need not worry about it. You will learn when you study measure theory, all these things, you will learn this. But for us, if you take, so just if you take finite or discrete, okay, Let us take omega 1, omega 2 are countable, okay, discrete. Then you need not worry about these things. Okay, then our sigma algebra is just omega 1 cross omega 2. Then you can take a power set of omega 1 cross omega 2, which is famous. Which is, yeah. And then you define P. You have P1, P2, where P of A1 cross A2 equal to P of A1, P of A2. I mean, this is clear, you can do it. This is for all. It's enough to define A1 cross A2 because here you are having omega 1 is countable, omega 2 is countable, so this cross product is also countable. Okay. On the other hand, this cross, similar, so it's enough to define this point mass, right? There is some, the point mass. You define P of any A. You have P of T. This probability here is given by point mass, right? A1 you have to a subset of omega 1. Okay. But any subset you can do this. A1 cross A2. No, I'm not talking about independence, time being. I'm just defining how to define the measure on that. So general case is different, continuous case is different, which is the product probability measure, which is not talking about. I'm just taking just discrete one, where omega 1 is countable, omega 2 is countable. Then you just take the cross product, omega 1 cross omega 2. Then you take the power set of that, then you take the P. Okay. You can define, for example, this P of any AB. Okay. Equal to P of P1 of singleton AB, which is defined like this, cross P2 of singleton B. Okay, here I will put the small one. Okay. Yeah, when defining this P. Then you define P, capital P of any set A cross B. You need not define A cross B for any A itself, which is equal to summation of all those AB. Okay. In A, you take the P of AB. Okay. Where A is in omega 1, B is in omega 2. Okay. This will give a probability measure. This is the product measure, product probability measure. This is trivial, no? You have omega 1, which is countable, omega 2, which is countable. You take any set subset of this. Okay. For the define the point mass to be just this. Because this is defined through point mass. This P1 is defined through point mass, P2 is defined through point mass. Okay. Discrete probability of a singleton set. We define, no? If we have some P probability, then P of A, I called it as P of A or whatever. Okay, this is the mass of that. Okay, usually it will be density because probability of a singleton will be 0 in a countable case. But in the discrete case, it's like a mass in the point mass. Okay, there is a mass like this. Okay, or weight or whatever. Mass is the right one to use, no right word to use. Okay. So the thing is, when you define like this, in this, if you have a, I have used A, maybe something else. If you have A contained in omega 1 and B contained in omega 2, then it is always the case, then A cross omega 1 and omega 2, B, omega 1 cross B are independent. Okay. Is it clear or should I write it? I think it's clear, right? You have one discrete probability space. This you can take it to be power set. You have a discrete probability space. You have another discrete probability space. Then you can define the product probability on omega 1 cross omega 2 like this, just by product. Okay. Then it is clear. Then the probability of this, probability of A tensor, A, I use tensor, but it's product. Okay. Tensor is actually it is tensor, but from my mind I may get the word tensor, but you need not worry about it. Probability of this is exactly probability of A. This is probability of A times probability of omega 2, which is 1. So which is probability of A. Similarly, this is probability of B. On the other hand, probability of A cross B, the intersection of this will be A cross B. which will be probability of A times probability of B, so they are independent. So if you have one coordinate, if you have another coordinate, they are independent. So this is how you can construct independent events. This is like you do one event and you repeat it independently. You toss a coin, and you take the same coin and toss it again. Okay, assume that that has no influence on the second experiment. First experiment does not have any influence on the second experiment. That's like you are repeating. So it's like repeating the same thing. Okay, so okay. Omega 1 is some set of subset. Then what do you want to do? I didn't understand the question. If you
independent with same.
how do you that we can do? That is generally if you have any probability measure, it's product or something. This is one way of getting independent sets. Okay. The reason I am doing it is because later I want to define you what is called independent random variables. I will use this example. You want to get two independent random variables, then I will use this. Okay, that is why. In general, if you have any set A and B, which are in the same probability space, same set omega 1, then they are independent if the product, the probability multiplies. P of A intersection B is P of A times P of B. That is the definition. This is a construction. This is an example. Hmm? Yeah, this is one example where the independent happens. Okay, so we want to define what is called a random variable. Okay, that is our next topic. So to define that, I will give you an example first. A random variable is like an experiment done over a probability space. You have a probability space. Okay, you have something. The coin, tossing a coin, for example, is the simplest probability space we can think about. And based on using that probability space, you do an experiment. What is an experiment? It could be, for example, you are standing here. You have numbers 0, okay, and you can only move one dimensional. You can do it in 2-dimensional, 3-dimensional, any dimension. Then it will be more complicated. For simplicity, we are assuming you can move to 1, 2, 3, 4, like this. Exactly, random walk. And you can come from -n to 1. Okay. What you do is you toss a coin, and if it is head, you move here. If it is tail, you move one step backwards. And you don't land up anywhere here in the middle. Okay. So head means one step ahead to go in the front. And tail means one step back. Okay. Where you are. I mean, then your position. What is your position at a point? After n trials or something. It could be n, it could be any one of these things. It will not be 0 because you would have moved somewhere. No, it can be, it can be 0. Yeah, it can be 0, right? Yeah, it will be one among them. Okay? From n to -n, well, it depends on n. Maybe not all possibilities are there. See, if it is even, for example, then it will not be the case, no? Yeah, exactly. It depends on whether it is n is even or odd. It depends on that. Okay. So we will calculate it. So this is a random walk. Here, the probability space, the random walk takes the values from -n to n. So there are 2n plus 1 possibilities. It's much less than that. It is n possibilities, I think. Okay, n possibilities. I mean, if it is odd, some possibilities are some numbers are not possible. If it is even, something is not possible. So I think it is n possible. We'll calculate it. Okay, so there are n possibilities or something. But on the other hand, for ht, the probability space is let's take ht. Omega is ht power n, which has 2 power n. The cardinality is 2 power n. There are 2 power n possibilities, but here we have only n possibilities. So the random variable varies within a smaller set. maybe much smaller, or so it can be a completely different set. Okay, so this is your probability space. You are doing an experiment on this, you are getting a different result. Okay, this is what is like a random. It's what is called a random variable. This wherever your position, which is a number, which varies, which is a random variable, which varies according to this probability. This is what is called a random variable. For example, you can throw two dice and then you can take the sum. You can take the sum. Whatever the sum you comes, you call that as the number. That is the experiment. Then it will be a random variable. Yeah. Exactly. That's what I'm going to define. So this is the definition. Okay. If omega, I'm writing the general definition, but we will be considering only discrete probabilities. Okay. So it's a probability space. You know the meaning of it. Probability space. Okay. Let omega be finite. Let omega be countable. Finite or countable. Okay. Countably infinite for the time being. Okay. Then any function x from omega to r. This R can be C or a vector space Rn, or it can be any space, okay, any vector space or something. Okay, whenever whatever you need according to your experiment, you can vary it. Then it's called complex random variable, or it's called you should call it in a different name. Okay, for the time we are using only real variables, so this is real random variables. Okay, any function is called a random variable. That's all. And this be C. I said anything you said. What? That will be a complex random variable, that's all. What you want to study based on that. We are going to study some particular probability distribution, particular random variable. So for that, we are using only real line. Okay. If you want to study, you can have vectors. You can even have sets. There is something called random sets. What is random sets? It's just a function mapping on sets. Or you can have a collection of sets. This omega can be a collection of sets, so you have a probability measure on that. Okay. Or surfaces. You can have anything you want. Okay. You just have to be able to define these things, and you should have enough tools to study that. That's all. Okay.
Defining the sample space to be minus into one and then defining
Our sample space is this. This is a function taking values here. X takes values. So in this case, omega is this. Okay. X is a function from omega taking values from minus n to 0 to n. X taking values here. X is the random variable. Random walk is a random variable. Okay. That's all. So random variable is just a function on omega. That's all. Okay. Okay. But let's say, I mean, you know that if the omega is countable, then x should also be countable, because a function is well defined. It can have only one image for a point, so it cannot be uncountable. The image cannot be uncountable. So say if this is general, any probability space. Okay, we are not assuming it's countable or something. Then x from omega to a is a random variable. Okay, if it's called a discrete random variable. I am not defining continuous random variable. Okay, discrete random variable if the range of x is countable. Okay. Let x of range of x is x of omega, right? X of omega, f of something, okay, which is equal to some x1, xn, yeah, like this. Okay, x1, x2. Okay, is a discrete random variable if one, first condition, and second condition is all those omega in omega, a function. If you define a function, a point, there may be many points mapping to one single point, right? It can be many to one. Okay, need not be one. Okay, so all omega such that x of omega equal to some xi. Okay, is in that set A. That's all. The point is we should be able to talk about this probability. We want to talk about the probability of xi. Okay, to talk about the probability of xi, all those omega which will be, see, the probability is defined on omega. Okay, it's on for subsets of omega. Xi is taking values in real line. Omega can be anything, head or tail or any set. Okay, you can contain anything. Okay, and but then Xi is a number. You want to talk about the probability of getting this number for a discrete random variable. That will be exactly the probability of this set. Okay, so we need to talk about the probability of this set means this set should be in the sigma algebra. That is the condition. That's all. No, we are defining a discrete random variable. You have already defined the random variables. Let me go through. We are already, you have a discrete probability space, then any function is a random variable. Discrete probability space. If you have a general probability space, it may be continuous or combination of both discrete and continuous, whatever. You can take union of two things. Okay, so it can be anything. So there, a function is a random variable. If a function is a discrete random, this is not general random variable. Function is a discrete random variable. If the range is countable, range is countable. Range of x. This is range. It's not writing the board. Okay, range of x is countable. Okay, that is x of omega, which is the range. No, x of omega is the range, which is x1, x2, something. It's countable. You can enumerate it. Okay, so when it is countable, for each xi, this set is in the sigma algebra. We should be able to talk about the probability of this set. This should be in sigma algebra. That's all. So even though the probability space here, the point is even though the probability space may be continuous, but we can actually talk about discrete random variable. The random variable may be discrete. Okay. Probability space may be continuous, but the random variable which is defined on omega may be the interval 0, 1 or something, but you take the random variable to be, it takes only countable number of values. Okay. This is all big omega. Small omega, I write like W. Huh? This is small omega. Sorry, yeah. Omega in omega. This is omega, no? Omega in omega. Such that x of omega equal to xi. Yeah, is in all those omega. You collect all those omega. Okay, that set is in A. That may be a single set or it may be a countable, uncountable set. It can be anything, right? Many things can map to one single point. Okay, all the pre-image of xi. This is just the pre-image of xi. Okay, the all set of all elements in omega which gets mapped to this xi. Pre-image of xi. That should be a measurable set. I mean, that should be in the sigma algebra. So that we can talk about the probability. Otherwise, we cannot talk about it. It's defined only on this. Okay, it shouldn't be very complicated set. That's all. That's the, if you, what is defined, random variable defined on omega, right? Yeah, then? This is contained in omega, right? This is all collections of subsets of omega. This is a collection, need not be power set, right? This is a sub collection. Script A is a sub collection. Okay, what's your confusion? That is what we are assuming. Right. Yeah, there is no other A. There is only one A. I haven't said any A in real line. This is the only probability space we have. There is no other probability space we are not talking about. There is no probability space. We will get a probability space, but we haven't talked about it yet. Okay, this is the only probability space we have. Omega script A P. This is the probability space. X is defined on omega. Okay, any function. Then you say it's a random variable. If it's the inverse image of these points, a single point or finite point also, it will be just finite union or right. I mean, if you take inverse image of any finite point also, it will be finite union of that. Oh, okay. Ah, so this is what your confusion. Sorry, sorry. There is no A. I am sorry. It's supposed to be. Yeah, you should have corrected me earlier, right? Oh, sorry. This should be real line. I'm sorry. Yeah, that's a real confusion. But you should have immediately clarified. I mean, I said no. It exists a real valued function, which I have said. No, this is just my this set. This is omega. This is subset of omega. What do you mean by omega? Oh, this is for a particular I. Okay, if you want. Okay. Okay. I'm sorry. Oh, is that your confusion? Okay. For a particular I, for each I, for all I. Okay. It should happen for all I. That's good. Good clarified. Yeah. Omega can be continuous. It's not countable. That's all. It's not just countable. Yeah. Now, when it is countable, you have a definition. When it is not countable, we need to deal with sigma algebra. So that's why I have written. That's all. It can be union of continued some interval and some countable finite points or something. It is possible. Okay. So that's why we don't call it continuous. It's just any probability space. This is general. That's all. If you have a general probability space, then the inverse image of this xi should be in this. Yeah. So this is for all I. You have a ai. This ai should be here. That's all. Inverse image of each point. I said it correctly, but when I mean, I didn't write what is, this is for all I. You fix a I, they should be here. For all I, each I, this is true. This statement holds for all I. This is okay. Huh? Of course, that's the range. So it should be omega, right? Yeah, if it is inside, if it is I, all I, then inside, if it is all I, then it is omega. But it's outside. Okay. So now it's okay. Yeah. Okay. Okay, so the definition of random variable is clear, but mostly we will be dealing with finite and discrete random variables. I mean, the probability space will also be discrete. Example. First example, you take omega to be n times you toss a coin. You toss a coin n times. So it will be ht power n, right? Direct product n times. You know the power. And I don't have to write the probability and all those things. That's clear. Which is maybe, yeah. Probability of single coin, probability of singleton. I mean, let's take omega. I mean, probability of H is P, probability of T is okay. In HT, in this space, probability of H is P, probability of just to be clear, is P, probability of singleton T is 1 minus P. Okay. Probability of head is P, probability of tail is 1 minus P. Then you take the n direct product of this. Okay, n direct product of this. So x is defined from, I mean, if you want, you call this as omega, call this omega n, doesn't matter, but we are calling this as this omega 2 up to n is just number of tails. X is x of any omega, which will be HTTT, I mean, kind of tuple like that, which is just number of heads. So omega will be something like this. H, T, 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 T kind of n tuple like this. Okay, consisting of these things. Okay. So we want to compute what is x of, I mean, probability of this set. Want to find probability of all those omega in omega such that x of omega equal to k. Okay. X of omega equal to k means number of head is k. Same thing as, no, here it is just 0 and 1. Random walk is between -1 and 1. Now this is just counting the number of heads. There tail will take you back, no? Here it's not like that. It is just number of heads. So it will take values from 0 to n. That will take from -n to n, right? Not all values, but some of the values, half of the values. Okay. It is just the sponge. Hope it's okay. Hope it works there. I don't know. Once again, I think it's working. I think it's working. It's not playing. It's testing. Okay. Okay. No problem. So we want to find this. Okay. So to find it, the probability of particular pattern, probability of some pattern, I mean some particular pattern with k heads. Okay. Some pattern. Pattern means it is just the T H. It's just the permutation of T and H with I mean whatever. H is identical, T is identical. Pattern with KH. Okay. That will be equal to P power K 1 minus P power n minus K. Okay. But then there are so probability of x of omega equal to omega. I mean, we need not write omega and omega something. When we write x equal to omega, x equal to k, by this we mean probability of omega in omega such that x of omega equal to k. Okay. For simplicity, we'll write like this. Probability with particular pattern. Particular pattern. Yeah, I said it, but didn't write. Yeah, good. Particular pattern is this. So for any pattern, it should be nck times p power k 1 minus p power n minus k. Okay. So this is a random variable. We have found this. This function. See, this is how we write probability of x equal to k. When you write probability of x equal to k, that means probability mathematically. That means probability all those omega, because probability is different on omega. Okay, so we are getting a new function, probability of x equal to k. It's something a probability distribution on real line on 1 to n. Okay, probability of x equal to k is probability of omega and omega such that x of omega equal to k. Okay, that is equal to this. This function on each 1 up to n is what is called probability density. It's not density means in continuous case it is different. So it's not exactly density. We call it as mass function, probability mass function. Okay. So definition. X from, when we have a probability space, I'm assuming probability space or a random variable. Okay. Then with when for x in R, okay, f of x equal to probability of omega such that x of omega equal to x. Okay. I mean, it's a discrete random variable, let's say. We are only dealing with discrete random variable. Then you define for x in R, f of x equal to this. we know that it's a discrete random variable, so it will take only countably many values. Okay, x1 up x1 x2 signed up, it's a countable values. But then this is different for all R. If it is not in one of those countable values, then the set will be empty. There won't be any omega which is mapped to that. So this set will be empty. So probability of empty set is 0. Okay, only probability of those xi's where I have written there, no? Where did I write? Somewhere here. Okay, this is the range of that random variable x. Okay, for all these xi's, this will be positive, or there also it can be 0. Okay, it's possibly 0, but it's greater than or equal to 0 on this set. Outside this set, it is 0. Okay, this is what is called probability mass function, or density also sometimes people use. Okay, this is called mass function. Probability density or probability mass. I mean, this is density is because density is something to do with continuous. It's from each point it has a mass, so it's better to use mass function. Okay, density of x. Okay. So x is a random variable which is defined on the probability space. Then you got a probability mass function on this, which defines the values like this. The thing is, sometimes you don't need to worry about the probability space. It's enough if you can work with just x and f. Okay, this f will define Ax. We'll see that. Okay, we can work with that. This example is what is called Bernoulli. Okay. Yeah. No. Bernoulli is one, no? But no. I think I have written it. Binomial. Okay, this is Bernoulli is one. And n equal to 1, it's called Bernoulli. Sure, you are right. Yeah. So this is called binomial. Okay. I mean, it is that whatever I'm going to write the probability density function, that is what is called binomial. Okay. So in the previous case, in the previous example, f of k equal to that nck p power k 1 minus p power n minus k for k equal to 0, 1 up to n, and f of x equal to 0 otherwise. Okay.
The mass function and for
Yeah. Uncountable, this is not useful. This is not useful. Extend which definition? You can't extend. This is not useful because all this f will be 0. I mean, if at all, if you want the real continuous one, then all this f of x will be 0. So it's useless.
sigma algebra, then it is increased.
No. If you want a continuous one, we consider the uniform one, which I have erased. Uniform probability 0, 1. Probability of single point is 0. Okay. Oh, you are talking about the random variable. Yeah, random variable you can talk about. No. If the random variable is continuous, it's useless. That's what I want to say. Sorry. For random variable, this is okay. This is defined for any random. There is no continuation or something. No. We are talking about the random variable or omega. Random variable is discrete. So further, this is useful. The random variable itself is continuous, which we haven't talked about. Then it's useless. Now, that is what the definition of continuous. I mean, it may not be that, but it can be that. There is a possibility like that. Huh? No, so in some probability space it is 0, no? Which x, if the x is continuous, the random variable is continuous. For example, you take this random variable 0, 1, and you take x of omega, use just omega. Okay? The probability of any point is 0, no? Here. Yeah, then it's a combination of discrete and continuous. We call continuous as combination of discrete, I mean, which is non-discrete, you call it as continuous. So I'm just saying in that case, this is not useful, I said. This can be zero, so this is not useful. It can be, it's zero for every omega. So there's no use for this. That's what I said. Okay. Exactly. Yeah, like that. The radioactivity or whatever. Yeah. Hmm. It can be non-zero, which is called again a mass. It can have a mass, but it need not have mass everywhere. If it has mass everywhere, then I mean it's only defined by the mass, then it's a discrete one. At some point it will be like that, no? I mean, it can have some probability zero, but then for a big interval or containing those things, it will be non-zero. Okay. It can be non-zero anywhere. Uh, you think about all this question. The point is that is not useful. That's all. Okay. If you think somewhere that taking this point mass is useful, you just tell me. Okay. You can have different situations. Okay. You can combine a purely discrete probability space and a purely continuous probability space and get a probability space. This may be anything can happen. Okay. Purely continuous means what I said here. Probability of every single point is zero. Okay. That is a purely continuous. Okay. You can take a combination of those things. Okay. So in the for this binomial, it is this. So when n equal to 1, that's what is called Bernoulli. Okay. We can get this Bernoulli from Bernoulli is just 2 point. It has only 2 points. One point has a probability p, the other one has probability 1 minus p, which you can get it from any probability space. Okay. For example, this is the one random variable which is called indicator random variable, simplest random variable. Okay. Indicator random variable. You take, this is anything, continuous or discrete or anything, any probability space. Okay. And A is any set in script A. Okay. Defined. I mean, instead of X, I am writing number 1. 1 is not number 1, just a notation. Okay. Please don't mind. 1 of omega. This is number 1. Okay. I will use I. I of omega. A of omega. Okay. This is okay. Indicator function of A. So this is the function. A of omega is 1 if omega is in A. Equal to 0 if omega is not in A. This is a function, right? If it is in omega, it takes the value. Sorry, if it is in A, it takes the value 1. If it is not in A, it takes the value 0. Okay, it vanishes outside the set A. This is certainly a random variable. This is a random variable means we have to verify two conditions. IA of omega is the image is 0 and 1. Okay, and the set IA, this is our X, okay, is in A, is in equal to 0, equal to A, equal to 1 is A. Okay, IA equal to 0. By this, you have read X equal to, I have written, no, this condition. We write it probability of X equal to K by this set. This is just a notation. This is equal to all those omega in omega such that IA of omega equal to 1. Okay. This is a notation. Probability IA equal to 1 is A. A equal to 1. That will be P of A. This is also okay. Okay. Similarly, IA equal to 0 is A complement. Okay. So it takes only two values. And we know if you want, you write probability of A equal to probability of A. And probability of this equal to probability of A complement. Okay. So this is a Bernoulli IA mass function. I mean, how the this binomial is for the probability mass function. Okay. So the F for this, F of 0 equal to P, 1 minus P, and f of 1 equal to p. This is the mass function. This random variable takes only two values. Okay. And the value and the probability, I mean, you can forget the probability space. There are only 2 points. For the first point, for the point 1, it is p, point 0, it is 1 minus p. Zero being, then you have to take IY complement. That's all. What you define here, you can define any number, you get this. It's better to define 1. You can take it, but it will not have nice properties. For example, when you do expectation, you want to get the measure of that set. It will not work. Okay. That's why we take 1. Okay. Okay. So this is like 2 point. It's a Bernoulli. Okay, Bernoulli is there. So you can, from any probability space, just fixing this set, you can get a Bernoulli out of it. Okay. This is an example also. From continuous, you can get a discrete one. And a continuous space, you can get a very simplest random variable. Of course, there is a constant random variable. Should I write it? A random variable whose image is just 1. I mean, one number. 1 means not number 1. Only 1. Okay. 1. any number. Any fixed number is constant. A constant function. A random variable, which is a constant function, is a constant random variable. Okay. I don't want to have to write. Okay. That whatever that set we are considering, x of omega equal to c, it will be whole set and probability will be 1. It's a kind of constant variable. It's a certain random variable. It will certainly happen. Okay, there is just, we use that notation, so I'm just saying. So I will not write it. If you want, constant function is if x of omega equal to c for all omega in omega, this is what is called constant random variable. Okay? Constant random. Okay. So let's see some more example. I will just orally tell you the situation. Okay, for us only the random variable and the mass function is important. So let me give an example and let me prove that. So properties of the random variable. So this is proposition is easier. So let x is a random variable. X is not a random. X is a random variable. Discrete. Let's say discrete random variable. Continuous also it will work, but let's take discrete random variable on some probability space. Then the f we associate with that. If you want, you can put a suffix x. Okay. I mean, it's up to you. It's when it is clear, you don't need to. Okay. So fx be the probability mass function. This is the mass function. Then fx satisfies the following property. 1, f of x is greater than or equal to 0 only, sorry, f of x is greater than 0 only for finitely many. Sorry, countably many. Okay. So f of x is greater than 0 for all x. Okay. X in R, and f of x is greater than 0 only for countably many. Okay. Okay. F of x is greater than or equal to 0 for all x. That is clear. It can be 0. It is strictly greater than 0 only for finitely many. Okay. Okay. This is okay, no? Only for countably. Huh? Okay. Shall I write it again? F of x is greater than or equal to 0 for all x in R, and f of x greater than 0 if only for finitely many, only for countably many points in R. Okay. What you don't understand? Why? Because range is only countably many, no? Only on those xi, there also it can be 0. It can probably be greater than 0, strictly greater than 0. So there are only countable. This is discrete random variable, okay? It's a discrete random variable. For discrete random variable, this is true. Okay. And the second condition is summation. This is a countable sum if you want, or you can use f of xi. Okay, where I mean the value of x of omega equal to some x1, x2 like this, or you don't need it. You can just write it like that, x and r, because it's zero only for non-zero only for finitely many. It's okay. It's only a countable sum. There's nothing wrong in writing like that. Okay, but if you want, you can. So I write it like this, or it is a summation of f of xi. Okay, so this is equal to 1, of course. That's all. These two properties are clear, no? Should I explain? So it's clear. Okay. Because if you sum it over, that will be, I mean, that is just the problem. These are all disjoint sets. Okay. Summation of f of xi I is equal to probability of disjoint union of this set x equal to xi, okay, which is omega, probability of omega, which is equal to 1. So this is clear. So this property is clear. The position, this is clear. The converse is what we want to do. So suppose x is any random variable with mass function, probability mass function f of x, f, okay. No, sorry. We just had the mass function. I'm not talking about random variable. Let f be any function from R, okay, R to 0, 1, okay, such that f of x greater than or equal to 0 and f of x strictly greater than 0. I mean, this is one thing, and for finitely, for countably many, it satisfies those conditions. That's what I'm just rewriting this. For countably many and summation f of x in R equal to 1, then there exists a probability space. The statement is longer than the proof. Okay, the proof will be very easy. Okay. There exists a probability space and a random variable x with, is it okay if I write it here? With mass function f. Okay. If you have any function with those two properties, then there is a probability space and random variable. When you have a random variable, it is different on some probability space. When you have any mass function means it satisfies those two conditions. It is only it's greater than or equal to 0, and it's strictly greater than 0 only for countably many, and its sum is 1. Okay. So then there exists a probability space and a random variable defined on that, so that its probability mass function is this f. Okay. Probability for mass function satisfies this property. When any function satisfies this property, that is actually a probability mass function of some random variable. That's all. So the proof is easier than, yeah, we'll go there. So, and past time, I forgot. Okay, then we'll stop. I have done very little of what I intended to do, but it's okay. We'll see it in the next class. This proof we will finish. Sorry, this proof we will finish. What I mean is, I have more. Yeah. I mean, I need more than 2 minutes to say whatever I want to say. I want to say many other things. We'll do it in the next class. This proof is very simple. So within 2 minutes, I will finish. Okay. This is just you take. So it takes only countable many value. So proof. Let x1, x2, xn like this, whatever, is equal to all those x in R such that f of x is strictly greater than 0. Okay, this is only countable by definition. Mass function f. Yeah, this is where I asked you whether shall I write it here and then wrote it here. Okay. So, probability mass function with f. Okay, f is the mass function. It is just the converse statement of that. Okay. Given a random variable, you have mass function. If some function satisfies this property, you have a random variable with that corresponding mass function. You take this to be f of x equal, this is countable set, so you take it to be like that. Then you take your omega to be this. Then what will you do? Then you define x from omega to r to be just f of, sorry, x of xi equal to xi. That's all. Okay. Then probability of x equal to x is precisely f of xi. Okay. That's all. That's all. These. It can be always it continues. It just have a jump at each point, no? Huh? This is not right continuous. What is right continuous? Right continuous means it goes and it continues with that. It doesn't, it becomes immediately zero. You are confusing with what is called distribution. Distribution is right continuous. This is mass function. This is not continuous. This takes only finitely many value. Okay. Yeah. This is not countably many value, whatever I mean.
My question being continuity was on the fact that like can f of x be integrable?
F of x will be integrable, but with respect to what? These are all, say, a single point you can integral will be zero. Riemann integral is zero. You need a different concept for integration. This is only a discrete thing, means you just need summation is the integral here. The integral you want to talk about is actually summation. Okay. This is a discrete probability space. So you will only sum. Okay. Exactly. There you will have density function which is different, which is not point mass, which is different, but you will integrate it. So that is why I am using mass function for this, density for that. Okay. So that no confusion.